Okay, this is section 2.6 from James Stewart's Calculus Early Transcendentals book, and it's a section on limits at infinity and horizontal asymptotes. I'm probably going to use 2 videos to present this material to keep the videos short. So first off, we're going to look at limits at infinity. When we're looking at limits at infinity, we're looking at as x gets larger and larger. Either in the positive direction towards positive infinity or in the negative direction as x becomes sufficiently large in the negative area. By definition, then the limit as x approaches infinity of f of x equal to L being a defined finite number, means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. So as x gets larger and larger and larger, the f of x outputs become really, really close. As you can see in some of these example graphs, the function outputs as x is approaching infinity become infinitesimally close or very close to the line y equal to L, and so our output would be L. And we would call this line y equal to L a horizontal asymptote, because asymptote by definition is your function graph would become very, very close as they move out along that asymptote. So we can have horizontal asymptotes, and we're going to find out that we find our horizontal asymptotes by taking limits as x goes to infinity and limits as x goes to negative infinity of your function. And if we actually get a finite number, then our function has a horizontal asymptote. We can also have vertical asymptotes, as we saw in previous sections, if after we reduce our rational expression or our function by removing common factors in the numerator and denominator, if we have the limit as x approaches a particular number of f of x, if that goes to positive or negative infinity from the right or from the left, then you would have a vertical asymptote. And in this course, we don't really address oblique asymptotes, which ends up being real number lines. All right. So again, the line y equal to L is called a horizontal asymptote of the curve if either the limit as x approaches infinity equals a finite number, or the limit as x approaches negative infinity of f of x also equals a finite number. And then we would say that y equal to L, which is a horizontal line, is a horizontal asymptote. Okay. At most, we can have 2 horizontal asymptotes for a function, because we really only have in the real number line positive infinity and negative infinity. So your function will have at most 2. Also, it is possible for functions to cross a horizontal asymptote more than once. You'll see in some instances involving trigonometric functions that they may cross an infinite number of times, and that's okay. However, your functions with vertical asymptotes, your functions will never cross a vertical asymptote. A vertical asymptote is a point of discontinuity. Okay, so now let's look at some examples and move forward on trying to identify our horizontal asymptotes. We begin with a simple function, the inverse tangent. If you recall, if y is equal to tangent of x, your input value, is going to be an angle, and your y is going to be a trig ratio, the opposite over adjacent in that reference triangle in the plane. And your y inverse, or your inverse function, inverse tangent, then is going to input the trig ratio and output an angle. And that angle, because our need to restrict our tangent function to be 1-to-1, that angle is going to be between minus pi over 2 and pi over 2. Good. And you'll see right here, this is the graph of your inverse tangent. And from the graph, you can see that inverse tangent of pi over 2 is going to be infinity. But if you input your trig ratio infinity, is going to approach pi over 2, right? Because if we input tangent of pi over 2, we would have a sine of pi over 2 over cosine of pi over 2, and that would go to 1 over 0, and 1 over 0, it's never really achieved, it is undefined, but it does move towards positive infinity. 1 divided by an increasingly smaller and smaller number does become larger and larger. So we do say that the limit as x approaches pi over 2 of tangent x is going to approach 1 over 0, which is going to approach positive infinity. Good. So we can use some examples here. Arctan is the same as inverse tangent of t. Okay, so if we were to calculate the limit as t goes to infinity of the square root of 5 plus 2 inverse tangent of t, we can see that as we're going to positive infinity, this is going to go to 5 plus 2 times pi over 2, and we can say that that is equal to 5 plus pi. Constants, the limit of a constant is a constant even when we are taking limits at infinity. With our second one, we can look at graphs of functions, and remember the limit of a composition of functions is the composition of the limits, and we can see here that we can say that the limit as x approaches positive 0 from the right, we can calculate our inverse tangent of limit as x approaches 0 from the right of ln of x. And if you recall the graph of ln of x, we have a graph that looks like this, and you can see that as x is approaching 0 from the right, our function outputs are going to negative infinity. So our calculation then is going to go to the inverse tangent of negative infinity, and that's going to approach negative pi over 2. Next up, in taking a look at the limit as x approaches negative infinity of sine, I want to note that let's take a look at the sine function. Oh, and I should probably give it in both directions, or even at that direction. Remember that if this is pi, our sine function looks like this, and it's going to oscillate back and forth, right? This is our y equal to sine of x. And is it tending towards a finite number, or is it oscillating back and forth? It's oscillating back and forth, so we would conclude that the limit as x approaches negative infinity of sine x does not exist. It doesn't equal positive infinity, it doesn't equal negative infinity, it will oscillate back and forth between values, at values between -1 and +1, and it will never tend towards a particular number or get infinitesimally close to a particular number, so we would say it does not exist. I'm going to hold off on the limit as x approaches infinity of sine x over x, because I want to discuss how to calculate limits at infinity with rational expressions first. So I'm going to move forward here, and this is that introduction. So we can take a look at our function y f of x equal to 1 over x, and we have that that function is this value, or that on the right of x equal to 0, and here is on the left of x equal to 0. And we can clearly see that the limit as x approaches positive infinity of 1 over x is approaching 0, right? Because this is our line y equal to 0. 1 divided by a bigger and bigger and bigger number is becoming smaller and smaller and smaller. It will never achieve the value of 0, but it will get really super duper close to it. So we do conclude that the line y equal to 0 is a horizontal asymptote, and that we define the limit of 1 over x as x approaches infinity to be 0. Same on the other side, we can see that our outputs of our f of x are approaching y equal to 0 from the right, or if as limit as x approaches negative infinity of 1 over x, we're approaching 1 over infinity, but negative infinity, and that is still going to be 0. And so y equal to 0 is a horizontal asymptote. In the previous section, we had the rule that if the limit of as x approaches a, and a can be infinity, of f of x is equal to L, then the limit as x approaches a of f of x to the nth power is going to equal L to the nth power for any n that's bigger than 0. So we have a theorem then that if we have the limit as x approaches positive or negative infinity of 1 over x to the n, that's going to equal 1 over x to the power n, and we can use our composition of functions and say, well, then that's going to equal the limit as x approaches infinity of 1 over x all to the power n, and that's going to be 0 to the n, and we're going to get 0. So that's a very useful rule as long as our r is larger than 0, because remember, with our exponent rules, we are going to find out, if we can take a look at if r is less than 0, then 1 over x to the r would be x to the minus r, and minus r would be bigger than 0, and the limit as x approaches infinity of x to the n, where n is bigger than 0, is going to be infinity. And we'll get to that a little later. Okay, but we're still going to make use of this property here. The limit as x approaches infinity of 1 over x to the r is going to 0. Okay, so now how do we evaluate these limits as x goes to negative infinity? Our first approach would, most of the time, we do want to kind of substitute our value of a. So we would kind of want to put these in there, keeping note that a number a times infinity for a bigger than or not equal to 0 is going to give a positive or negative infinity, and that means a can be positive or negative. An infinity plus an infinity is still going to give you an infinity. And infinity plus any number or minus any number is still going to give you infinity. What you can't determine right now are our indeterminate forms for these infinities. We can't have infinity divided by infinity, and we can't have infinity minus infinity, and we can't have infinity times 0 for the moment. So that's when we have those indeterminate forms, that's when we are prompted to algebraically manipulate. And we'll explain or cover more indeterminate forms and cover more limits when we get to Chapter 4, applications of the derivative, and that's when we'll talk about another technique called L'Hopital's rule. But not now. We're still just dealing with our limit laws and knowing how to calculate our limits. So let's take a look at this one. And remember, we also have a rule, the limit of a product is the product of the limits. And remember when we got 0 over 0 as x approached a, then a would be a 0 of the top and a 0 of the bottom. And we could then say that x minus a is a factor of the top and a factor of the bottom, and we would factor the numerator, factor the denominator, and cancel those equal magnitudes of 0, and then be able to find a limit. And when we did remove those common factors in the top and bottom, that 0 in particular became a hole in our graph, and it was a point of discontinuity. So in this case, when we go to infinity, you know, if I were to, in this case, plug in my negative infinity, I would get 1 minus 7 times minus infinity to the 5th power over minus infinity to the 6th plus minus infinity minus 7, and I'd be getting some sort of infinity over infinity, and that's not going to be helpful. So what is my approach? I want to factor out equal magnitudes of infinity and then be able to calculate my limit, okay, using those limit laws. So I find that the highest power of x in the entire expression is x to the 6th. So I am going to factor out x to the 6th everywhere in the expression. So if I factor out x to the 6th from the numerator, I'm going to get x to the 6th times 1 over x to the 6th minus 7 times 1 over x, right? Because if I were to multiply through, I would actually get back what I started with, or just remind ourselves, how would we simplify 3x plus 6? If we wanted to factor out the 3, that would be 3x divided by 3 plus 6 divided by 3. So we're just dividing out by x to the 6th in the same way, and we would end up with x plus 2. Good. So that if we distributed the 3, we would end up with what we started with, just as an example. So here we pick our highest power, so we want to factor out highest power from the top and bottom. Okay, so that's what we have first in the numerator, and now I'm going to do the same thing in the denominator. So in the denominator I have x to the 6th, and I would get 1 plus x divided by x to the 6th is 1 over x to the 5th, and then minus 7 over x to the 6th. I can then cancel my equal magnitudes of infinities, because I'm taking my limit as x goes to negative infinity. And now I'm going to employ this rule up here. The limit as x goes to infinity of 1 over x to the r is going to 0. And the other limit laws that I have, the limit of a constant is a constant. The limit of a constant times a function is the constant times the limit of a function. The limit of a quotient is the quotient of the limit. So I can actually put this limit everywhere into this expression. I don't have to write it out, but I can say that 1 over x to the 6th is going to go to 0. Negative 7 is going to minus 7, and times 1 over x is going to 0, and the denominator is going to 1, and we have 1 over x to the 5th is going to 0, and 7 divided by x to the 6th is going to 0. So our limit is going to go to 0 minus 7 times 0 over 1 plus 0 minus 0, and that's going to give us 0 over 1, and 0 divided by 1 is 0. Okay, so we can conclude that since the limit as x approaches negative infinity of 1 minus 7x to the 5th over x to the 6th plus x minus 7 equal to 0, 0 is an L, so y equal to 0 is a horizontal asymptote of this function. Okay. Same idea here. I see that x to the fifth is my highest exponent in the entire expression, and I'm going to calculate by my limit as x goes to infinity. I'm going to factor out the x to the fifth. So this is going to equal x limit as x goes to infinity of x to the fifth times 1 over x to the fifth minus 7. I'm going to factor out the x to the fifth here, and I end up in the denominator 1 plus 1 over x to the fourth minus 7 over x to the fifth. I'm going to cancel my equal magnitudes of infinity, and now I'm going to use my limit laws and say, and my new theorem, 1 over x to the fifth is going to 1 over infinity, and that's going to 0. And 7 is going to 7. 1 is going to 1. 1 over x to the fourth is going to 0. And 7 over x to the fifth is going to 0. So my function's limit as x goes to infinity is going to 0 minus 7 over 1 plus 0 minus 0, and that's equal to minus 7 over 1, which is equal to minus 7. So conclusion, y equal to minus 7 is a horizontal asymptote of that function. All right, here, if I were to plug in infinity, note that just for the sake of graphs, and it's easier to determine the limits of functions from graphs. Remember, we have a vertical asymptote there. Our graph of ln of x looks like this, and this is headed towards infinity, positive infinity. So as x approaches infinity, of your ln of x is going to infinity. Very slowly, but it is going to infinity. So if I were to first calculate the limit as x goes to infinity of the ln of x plus 1 minus the ln of 2x minus 1, I would get that I'm going to the ln of infinity minus the ln of infinity, and that's going to infinity minus infinity, and we have a problem. Okay, so when we do get problems, then we need, just like with 0 over 0 or infinity over infinity, we need to algebraically manipulate. So I notice that we have a log property, ln of x minus the ln of y equal to the ln of x over y. I'm going to use that to rewrite my limit as x approaches infinity of ln of x plus 1 over 2x minus 1. And that's a limit of a composition of continuous functions on their domain. And we have that this is going to equal the limit, or the ln of the limit as x approaches infinity of x plus 1 over 2x minus 1. And we'll want to factor out our highest power. And we can factor out our highest power, which is x. So if I factor out an x from the numerator, I would get x plus 1 over x. If I factor out x from the denominator, I get 2 minus 1 over x. I can cancel my common x's and then end up with ln of, and 1 is going to 1, 1 over x is going to 0, 2 is going to 2, and 1 over x is going to 0. So this is going to the ln of 1 plus 0 over 2 minus 0, and that's going to the ln of 1/2. So that's going to be our horizontal asymptote there. Okay. I'm going going to do this very first one. How do we find our vertical asymptotes and our horizontal asymptotes of f? And here we go. Okay, so how do we find our vertical asymptotes? We will want to take a look at what are the zeros here. What are the zeros of the denominator? The zeros of the denominator are when x squared minus 1 is equal to 0. And if we have x plus 1, x minus 1, then we have x equal to minus 1 and x equal to 1. These may be vertical asymptotes. Okay, so we will want to see which ones are vertical asymptotes. Maybe not all. So we just check. Okay, so those are the contenders for vertical asymptotes. And remember, if the limit as x approaches a, which is a finite number, goes to positive or negative infinity, then we will have a vertical asymptote. Okay, so let's first try x equal to negative 1. So if I have x equal to minus 1 of 4x squared plus 12x plus 8 over x squared minus 1, that's going to go to 4 times minus 1 squared plus 12 times minus 1 plus 8 over minus 1 squared minus 1. And what does that give me? That gives me 4 minus 12 plus 8 over 1 minus 1. Right? And that tells me that I'm going to get 0 over 0. So I know that x equal to negative 1 is a 0 of the top. It's also a 0 of the bottom. Or in other words, x minus minus 1 or x plus 1 is actually a factor of the top and the bottom. So I'm going to continue finding my limit, the limit as x approaches minus 1, and now I'm going to factor the numerator, and that is 4. If I factor out the 4, I get x squared plus 3x plus 2. If I factor the denominator of x plus 1 times x minus 1, that's going to equal the limit as x approaches minus 1 of 4 times x plus 1 times x plus 2. And we have x plus 1 times x minus 1, and I'm able to cancel the factor of x plus 1 from the numerator and denominator, and now I can calculate my limit and plug in my value, and that's going to 4 times minus 1 plus 2 over minus 1, and that's going to equal 4 over negative 2, which is negative 2. So we do have a limit that exists. So x equal to minus 1 is not a vertical asymptote. However, it is a hole in the graph. X equal to minus 1 is a hole in the graph. The function output does not exist, but the limit does exist. The limit from the left will equal the limit from the right. Continuing down, I'm just going to take this aside. Now I'm going to continue with taking the limit as x approaches positive 1. The limit as x approaches positive 1 of 4x squared plus 12x plus 8 of x squared minus 1. We can remove and we can still say that this does equal the limit as x approaches 1 of x plus 2 times 4 over x minus 1. And I note here that this is going to 3 times 4 over 1 minus 1, and that is going to give me 12 divided by 0. And if I can actually take a right-handed limit or a left-handed limit, if I choose a right-handed limit, then this is going to technically be a 0 from the positive side, and we're going towards positive infinity. So conclusion, x equal to 1 is a vertical asymptote. So in general, you will want to in calculating vertical asymptotes, reduce your rational expression as much as possible, and then whatever zero you cannot remove from the denominator, that's an irremovable discontinuity, will become a vertical asymptote. But note that we had two zeros, but one of them was removable. In other words, I was able to factor that zero from the top and the bottom. That becomes a hole in your graph. So how do we find horizontal asymptotes? To find horizontal asymptotes, we want to find all of them if possible, and there's only two of them. We want to take the limit as x approaches infinity of our f of x, and we also want to take our limit as x approaches negative infinity. So in taking the limit as x approaches infinity of 4x squared plus 12x plus 8 over x squared minus 1, we notice here that x squared is our highest power, so I'm going to factor out the highest power. So I'm going to say this is x squared times 4 plus 12 over x plus 8 over x squared. And I'm going to factor out the x squared from the denominator, and I'm going to get 1 minus 1 over x squared. I am able to cancel my equal magnitudes of infinity, and this is going to equal the limit as x approaches infinity of 4 plus 12 over x plus 8 over x squared, all over 1 minus 1 over x squared. And now I'm going to take my limit laws, and I see that 4 is going to go to 4, 12 over x is going to 0, 8 over x squared is going to 0, 1 is going to 1, and 1 over x squared is going to 0. So this limit is going to 4 plus 0 over 1 minus 0, and that's going to 4. So conclusion, y equal to 4 is a horizontal asymptote. All right. If we go to, we would do the same thing going to negative infinity. So if we did limit as x approaches minus infinity, we would still have the 4 plus, we'd do the same process, so we would still have 4 plus 12 over x plus 8 over x squared, plus 1 minus 1 over x squared, and we would still do the same analysis. 4, as x goes to negative infinity, is still going to 4. 12 over x is still going to 0. 8 over x squared, or 8 over infinity squared, is going to 0. 1's going to 0. And 1 over x squared is also going to 0. So we have the same horizontal asymptote. We just have one. Okay. I'm going to stop here, and I will continue with the part 2.